probability. In this video, we'll be learning more about probability and few other things. Again, we'll work on example just like how we have done in the previous videos. Why do we are going through this? Because it is an important topic when you go on to the machine learning and artificial intelligence. We basically talk lots about probability when we are taking accuracy. So like accuracy or how good a model is. So based on the probability itself, we can tell about the like probability would be nothing but percentages of how good we are getting accuracy and how good your model is performing. So that goes again down to accuracy. So probability is an important factor. So we have to be more attention with respect to this video because it dominates a lot with respect to machine learning. So what is probability? So a probability is a quality or a state of being probable and the extent to which something is likely to happen or to be a case. So let us see a basic definition of it. So as just mentioned, the quality or the state of being probable, the extent to which something is likely to happen or be a case. So it is like the chances of something happening or not. Okay. So basically, that is chances of event to occur or not. So look, we can quantify in terms of fractions, decimals, or in terms of percentages also. So the probability is an event happening between the 0 and 1. Okay, so it is the value is always from 0 to 1. So basically, this can be represented in terms of percentage also. So if you are telling 50%, so that will be equivalent to 5% when it comes to that will be equivalent to 0.5 value. Okay, so that is why we will be having. So for example, you have 0.9, so that will be 90%, and 1 stands for that, and how you're going to convert the fractions to decimals to percentage, it's all individual. So 0.5 can be written as 1 by 2 also. So everything can be represented using probability. So value is ultimately, if you are representing in decimals, it will be between 0 and 1 itself. It doesn't go below 0 or it doesn't go beyond 1. Okay, so it is minimum is 0% or maximum is 100%. So here we can see some kind of value. So here impossible. So definitely we won't be getting something like this. So which is very highly unlikely. So next is like a die. We'll see examples and like even chances and likely. So like 4 in 5 chances of the thing. And finally certain. Okay. So this is a simple a one-dimensional diagram explaining. So basically we won't be reaching any impossible state. Okay. So probably it is close to 0. Okay. So if it is impossible, it is directly 0. Okay, and certain is 100%. So now, how do we calculate it? Okay, so let us consider an event. A will be equal to event that you want to find the probability of. It can be any different event. Okay, so in the event, the probability can be denoted as P of A. Okay, so P bracket A. So that will be the probability of A. And the formula is pretty simple. It is just the number of favorable outcomes to A divided by total number of outcomes. So we'll look. We are looking to a sum to understand the formula better. So the probability of getting ahead for a, like, we'll see a basic sum as I was telling. So the probability of getting a head for a fair or unbiased coin. So unbiased coin over here. So it is a fair and unbiased. So basically, it tells it is not manipulated. It is a fair, assuming it has only two sides, head or tails. So we'll be finding a probability of getting a head when we are tossing the coin. So the answer is nothing but getting the heads. So putting down the formula, the favorable outcomes divided by total number of outcomes. Now I would like you, like everyone, to take a second to just understand like what is our favorable outcome. So how many times it should will come, and what is the number of outcomes. So you can pause a video, think for a second, and come back. So let me continue. So basically here the favorable outcomes is nothing but getting a head, right? So that is what is we are intending to find out the probability. So that will be 1. Okay, when a coin is tossed, you will be getting only one particular case where you will be getting head, and the total number of outcomes would be nothing but it can be either a head or a tail. So basically it can be either like it has two conditions, either head or tail. So that will be the total number of outcomes. So basically, probability of A would be nothing but 1 divided by 2 or zero point 0.5 or 50%. So this is what I was talking in the previous slide about representing with respect to a fractional part or a definite decimal part or in terms of percentage. Okay, so you can define in three different ways. So most easier way is like with respect to decimal and 50%. So having something like 1 divided by 17, so that doesn't give much insights when it comes to much insights when compared to having in terms of percentage or decimal, where percentage or decimal is almost one in the same. So that is a basic example. So we'll take another example. So now we'll just tell what is the probability of not getting a head from a fair coin and unbiased. So remember, it is unbiased, so it should not be it is not manipulated. So basically here not getting a head or is equivalent to nothing but getting a tail, right? So we are trying to find the probability of getting a tail and considering it as a unbiased form. So the formula is same as it is. So P of A will be equal to favorable outcomes divided by total number of outcomes. So again, the favorable outcomes uh, will be how many times we can get in head when we toss once. So basically, definitely we'll be getting only once. Okay, so that will be our favorable outcomes, and number of total outcomes we already saw. So that will be 2. So again, the probability of getting a tail is same as probability of getting a head, which is nothing but 50%. So this is like again, you can consider this type of data set as binomial. So over there you'll be having two outcomes. So here, even in this data set, it is either head or tail. So you can do for 10,000 times. Maybe you can have three coins tossing at the same moment. So you can have a set uh, like that, and also that's how the bigger data set will be acquired or something like that. So basically, as I was telling, it is under a binomial data set, so it has only two possible outcomes. And again, we'll see a probability of rolling a die. So again, an unbiased die. So basically, a die. I hope everyone knows what is a die is. So it will have six faces. Six faces will have numbers from 1 to 6. So 1, 2, 3, 4, 5, 6. So here we wanna, the example is like nothing but to find the probability of getting 4 in a roll of a die. So it is a single roll, and what is the probability of getting. So I think it is pretty straightforward. It is not that difficult. So I just want everyone to just uh, pause the video over here or something like this. So basically, a hint over here is nothing but the condition is over here is unbiased has equal chances of getting any of its sides. So it is equal chances. So again, it's not tampered or in any way. So it is unbiased and a fair die. So which means that all the sites are equally likely to occur. Okay, so just pause the video over here and figure out the favorable outcomes and total number of outcomes. So assuming everyone has paused the video and I have come back and figure it out. So let us see what exactly we will be getting. Let us consider A as getting as 4, and the probability of A is nothing but 1 by 6. So one getting, like when you toss a die, so definitely when you roll a die, you will be getting 4 only once, the one outcome of occurring. So and also the total number of occurrings is 6. Now we'll be seeing some concept known as union and intersection. So basically, this is a very easier one. It is not that difficult. So basically, here it is represented using a kind of the letter U and inverted U. Okay. So the first line it says that A intersection B. So A intersects B is nothing but the area of event A is intersecting with the area of event B. Similarly, we have union. So basically, that is the entire area of A and B. Okay. So again, we have some kind of properties for this. So basically, A intersection B can be nothing but probability of A multiplied with probability of B, and A union B is nothing but probability of A plus probability of B minus probability of intersection. So usually the union would be, probability would be unity, so it will be 1. Okay. So if at all probability of A and probability of B are the only two occurrings. Okay, so you can consider here the probability of A and B as nothing but tossing a coin which has 50-50%. and subtracting, like the coin might not land up in between, so intersection is not there. So again, a diagram would give us much more insights. A figure will always give a lot of info. So basically here we have kind of two people. Okay, so Alfred and Bruce Wayne. Okay, so you can consider Alfred and Bruce Wayne over here. And when it comes to the probability of having murdered parents, yes, both are murdered for those uh, personalities, and also they are incredibly rich. Okay, so the Venn diagram is overlapping. So here the outcome, what I wanna tell everyone is this: this black region over here tells the intersection of murdered parents with Alfred, or you can consider Bruce Wayne. So this is the region which is covering up. Similarly, incredible wealth is something like this. So even this intersection can be more or less. Okay. So based on here, we are just considering how wealthy they are, maybe some kind of proportions with respect to them, also like how common they are in. Okay, so that is with respect to Alfred and Bruce Wayne. Okay, so this is the probability telling that of getting union. So basically, this is the intersection, and union is nothing but the whole. Okay, so uh, probability of, maybe we'll consider with respect to murdered parents with Bruce Wayne. Okay, so over here, this complete two circles should be enclosed. What happens is when you're adding the murdered parents and Bruce Wayne, okay, so over there both circles are added up, and this part is repeated twice. Okay, so it is a part of murdered parents, so that will be included in P of A, and this part is also included in Bruce Wayne, so that is the probability of B if you're considering probability of A and B for murdered parents and Bruce Wayne, and this part is repeated twice, so hence we'll be subtracting probability of A intersection B. Okay, so this symbol, you can remember this U as union, and the complement or the inverse of it is intersection. Okay, so just remember that. Like that's the way how I remember the difference of symbols of union and intersection. So let us see examples which will give more insights. So now let us consider a playing card deck which will have 52 playing cards. So what is the probability of getting a jack and a heart? Okay, J of heart. So at that scenario, we have to like here again. It is a known fact that there will be four suits in a deck. Okay, so for four different symbols, so like heart, diamond, and nut, and each suit will have one jack each. Okay, so there would be only, but there is only one out of 52 when it comes to jack and heart. So what is the probability? Let us test it out. Excuse me. So with respect to Venn diagrams, so let us consider the probability of A first. So probability of A here we are considering with respect to the number of jacks in the playing card deck. So basically that is 4. 4 divided by 52 is nothing but 1 out of 13. Okay, so every suit will have 13 cards. So one jack is present in it. And probability of B over here is getting a heart, and 13 cards out of 52 cards would be of heart. So again, that was probability of 1 by 4. So and finally, if we just find the intersection of it, so it is like 1 divided by 13 into 1 by 4. So that is nothing but 1 divided by 52. So initially we actually already had the probability of this. So a number of the favorable outcomes is only one. So you have one unique card which is Jack of Diamond, and out of total number of deck or the possible outcomes is 52. So we just verified that A into B is equal to A probability of A intersection B. Okay, so the previous whatever properties we saw, and this will be the diagram. So here we have 1 divided by 52. Okay, it is not 1. Over here it is 1 divided by 52, and this is A and this is B. You can consider this as 1 by 13 and this is 1 by 4. So the intersection part is 1 by 52. And next is we can consider again there is 52 cards. So what is the probability of getting the jack? So basically we'll move the other way around, first checking with respect to the intersection. So probability of A is again 1 by 13. Sorry, jack is 1 by 13 and heart is 1 by 4, and intersection is 1 by 52. So basically putting down that into formula is nothing but 1 divided by 13 plus 1 divided by 4 minus A intersection B. So probability of A plus probability of B minus probability of A intersection B. So in the previous slide itself we had evaluated this, and also we have just written down it over here. So 1 by 13 plus 1 by 4 minus 1 by 52 will give us 16 out of 52 combinations, and ultimately will be having 4 by 13. Okay, so that is the 4 by 13 with respect to the union. Okay, so the union of probability of getting both. Okay, so that is the actual probability of getting jack and a heart. Okay, so that is like union having both jack and a heart. Next example. So here I want you to think hard on this question. So basically the question says that what is the probability of getting a 4 and a 6 in a roll of die. So consider it as unbiased. So just take a minute. So if you think exactly over here, what is exactly is happening is we can't get two outcomes out of one single roll, right? So it is telling a roll. In a roll, so basically we can either get 4, we can either get 6. The probability of them is 1 by 6 and 1 by 6, but we can't get both. So the question seems like wrong, but it isn't. But in real life examples also you will be facing such situations. With our instincts, we can say it is like 0. Okay, but when you have created a machine learning model, so that cannot directly identify whether it is correct or not, so it will go ahead and compute. Okay, so let us also compute with respect to that. So event a can be event where 4 occurs, and b can be event where 6 occurs. So intersection of them at same situation is 0. Since there is no intersection, so p of a intersection b will be equal to 0 itself. Okay, so that is nothing but that is how we represent in Venn diagram. So you can see there is no intersection, but they might be the endpoints are joined over here, or you can write them apart also. So basically they are not intersection. So the probability of A intersection B is 0. So I think we'll pause with this video. We'll be seeing conditional probability in the next video.